Hey guys, welcome back to another video. This is topic 2.4 Exponential Function Manipulation. The properties of exponents that you learned in algebra can also be used to manipulate or rearrange exponential functions into an equivalent form. Here's a review of important exponent rules. The first one is the product property, which says that b to the power of m times, there's an imaginary times here, times b to the power of n is equal to b raised to the power of m plus n. So all this means is that if you have the same base and the two numbers are being multiplied together, all you need to do is add the exponents. Okay, so for example, we have x to the power of 5 times x cubed. You grab the two exponents, 5 plus 3, add them together, you get x to the power of 8. Or we can have 2 to the power of x times 2 cubed. You grab the x plus 3, and you can't simplify any more than that because they are not like terms. Okay. Next, we have the power property. This is when you have a power raised to another power. Okay, so notice we have b already to the power of m and then again to the power of n. So this is when you have a power raised to another power. And when that happens, all you're going to do is multiply the exponents. So for example, x to the power of 5 all cubed, you would grab the 5 and 3, multiply them, and you would get x to the power of 15. Or 2 to the power of x cubed can also be 2 raised to the power of 3x. So you just multiply those. Okay. Additionally, the order that you multiply doesn't matter. So this could also be 2 cubed raised to the power of x. So sometimes it'll be more helpful to have the number inside of the parentheses because then you can multiply this, and 2 cubed would be 8 to the power of x. Okay, so you can have the variable inside or outside, but sometimes it's more helpful to have the variable outside so you can simplify the base. And then similarly here, we can grab this 2 cubed, which is 8. So then the final answer would be 8 with a base of 2 raised to the power of x. Okay, so you can simplify these even more. Now all of these, you should be able to do them forwards and backwards. So if I just give you this, you need to analyze the exponents, right? So if you look at the exponents and you see addition, that means you're going to use the product property. If you see multiplication, that means you're going to see the power property. And then you just separate them like this: b to the power of m times b to the power of n. For this one, I tell my kids, if you see multiplication, just separate the multiplication with your own set of parentheses like this, and then you see that you end up back with the original. Okay. Another property is called the negative exponent property. For this one, all you're going to do is take the reciprocal and then you're going to make the exponent positive. So we know that every whole number is divided by 1. So b to the power of negative n is being divided by 1. So to take the reciprocal, all you're going to do is flip these around. So notice that the 1 now is in the numerator. And when you put this in the denominator, you're going to make the exponent positive. Okay, so that's how you get rid of a negative exponent. So again, here's another example. X to the power of negative 3 is divided by 1. Flip it around, take the reciprocal, you get 1 in the numerator, and then the negative 3 becomes positive in the denominator. Okay, 2 to the power of negative x, always divided by 1. You flip it around, take the reciprocal, the 1 is in the numerator, and this negative x becomes a positive in the denominator. Okay, now this property is especially important because on the AP test in the instructions, it will say simplify with no negative exponent. So it's important that you know how to apply this property. There is another one that wasn't mentioned here. It's called the fractional exponents property, and this one is also important. This one says if you have the nth root of a number inside raised to another power, you can write it as whatever the base was inside of the root, and then the exponent would be m divided by n. So whatever the exponent was on the inside, you would put it on the numerator, and the root goes on the denominator. Okay, so for example, let's say I give you the 6th root of x to the 5th power, you would write x to the power of 5 divided by 6. Now remember, all of these you should be able to do them forwards and backwards. So if I instead give you 32 raised to the power of 1 over 5, you would write that as the 5th root of 32 raised to the power of 1. And we know that anything to the power of 1 is itself, so this is really just the 5th root of 32, which we know is 2. Okay? Okay, so make sure you memorize those properties. Remember, on the AP test, you do not have a formula sheet, so you do need to know how to do these without looking at your notes. These same exponent rules can be used when working with horizontal transformations of exponential functions. So let's review the format for transformations. So we have f of x is equal to a times whatever your rate is, your common ratio, since this is an exponential function. And then as the exponent, we're going to have our b times x minus h plus k. Let me bring this down a little bit. Okay, so from lesson 1.12, when we learned transformations, we know that when you multiply on the outside, you have a vertical dilation. When you multiply on the inside of the parentheses, you have a horizontal dilation. When you subtract or add in the parentheses, you have a horizontal translation. That means you're moving to the left or to the right. And when you add on the outside of the parentheses, you have a vertical translation. So you're moving up or down. Okay? So what they're asking us here is about horizontal transformations. Remember that all of your horizontal transformations are always in the parentheses with x. It's just that because it's an exponential, the variable is always an exponent. So that's why all the horizontal transformations are now raised to the exponent of whatever the rate was for the exponential function. So example 1 says determine the horizontal transformations of each of the following exponential functions. Okay, so I see that I have, and if you want to, you can always add parentheses around the exponent. They don't have to put the parentheses, but if that helps you, you can do that. Okay, so I see that I have x plus 2. So remember, when you add or subtract inside of the parentheses, that means that it is a horizontal transformation, and that is represented by the letter h. Now remember, also everything inside the parentheses is not what you think it is. So when you're adding, you're actually subtracting, and when you're subtracting, you're actually adding. So h here is actually equal to -2 instead of +2. So the original function, if I get rid of the 2, would just be 4 to the power of x. So that means that 4 to the power of x is being shifted 2 units to the left. Okay, now let's look at b. Again, if you want to add parentheses, you can. When you multiply inside of the parentheses, that would represent your letter b. That is, like we talked about earlier, a horizontal dilation. But again, remember, everything inside the parentheses is not what it appears. When you're working with b, instead of flipping the sign, what you're going to do is take the reciprocal. So instead of 3, you have 1/3. Okay, so the original function would be 2 to the power of x, and it is being horizontally dilated by a factor of 1/3. Okay, now let's look at C. We have 9 to the power of x divided by 2. We know that dividing by 2 is the equivalent of multiplying by 1/2. So I'm going to rewrite it as 1/2 times x. It makes it easier to see what you're multiplying by. And then again, when you're multiplying, that means that's the letter b. And then b is always the reciprocal. So instead of 1 over 2, it would be 2 over 1, which is just 2. Okay, so the original function would be y equals 9 to the power of x is horizontally dilated by a factor of 2. Okay, last one. If you want to add your parentheses, you see that we're subtracting 1. So that would be a horizontal translation. So that would be the letter H. And remember, it's always the opposite. So instead of -1, it's actually going to be a +1. So the original function 5 to the power of x is shifted right 1 unit. Now, let's re-examine the exponential function from example 1a and see if we can use our exponent properties to rearrange the function into an equivalent form. We can use the product property in reverse to show that 4 to the power of x plus 2 is equivalent to 4 to the power of x times 4 squared. Okay, so remember when you have addition in the exponents, that means you're going to use the product property. And to use the product property, that means that you keep the same base, but you're going to separate the exponents. So you have 4 to the power of x times 4 squared. Now remember from example 1, we said that this one had an h value of -2 and it was going to the left 2 units. Okay, but when I simplify this one, we have 4 to the power of x times 4 squared. We know that 4 squared is equal to 16. So now we end up with 16 times 4 to the power of x. But this 16 on the outside of the parentheses with x is by itself, okay? So x right now is by itself, so there is no horizontal transformations. When you multiply outside, that means that is the letter A, which represents a vertical dilation of a factor of 16. So we're saying that all of these are equivalent, but they look completely different and the transformations are different. How can we say that if we go to the left 2 and we apply the product property, now we have an equivalent expression, but it's now vertical dilation of 16. So let me graph it for you so you can see that they are actually equivalent to each other. So I'm going to add a graph, and I'm going to graph first 4 to the power of x plus 2. Okay, there you have it. Now I'm going to graph our final answer, which was 16 with a base of 4 raised to the power of x. And they are equivalent. So even though they look different, if you apply the properties of exponents correctly, you would still get the same graph, even though the equations and the transformations are different. Okay. So this means that f of x is equal to 4 to the power of x plus 2 is equivalent to writing f of x equals 16 to the power times 4 to the power of x. When we rewrite the exponential function in this way, there is no longer a horizontal translation, but now we have a vertical dilation by a factor of 16. So the important idea is that every horizontal translation of an exponential function is equivalent to a vertical dilation of the exponential function. Okay, so the horizontal dilation again is left and right. So you can go from having something in the parentheses indicating that you're going to the left or to the right, and if you apply the properties, it's the same thing as multiplying by a factor of a on the outside of the base, which is the equivalent of a vertical dilation. Okay. So example 2 says each of the following exponential functions has a horizontal translation. For each, write an equivalent representation that has a vertical dilation and no horizontal translation. Okay, so we want to get this in the general form for an exponential, which we have been talking about. The general form is just a times b to the power of x. So notice that all of these have addition or subtraction in the exponent, which is indicating left or right translations. And so we're trying to use the properties to get rid of those left and right to write an equivalent representation that has a vertical dilation instead. Okay, so remember that when you have addition in the exponents, you're going to use the product property. So I know that I can rewrite this as 2 to the power of x multiplied by 2 cubed. 2 to the power of x cannot be simplified, but 2 cubed is 8. Okay, so I can write this as f of x, and usually the vertical dilation is always in the front. So the vertical dilation is 8. My base is 2 and is being raised to the power of x. Now you cannot multiply these together, okay? The base of 2 is attached to the exponent of x, so these are a unit the same way that you wouldn't add 8 plus 2x, okay? Those are two completely different things. So please do not multiply 8 times 2. Okay, so that is the final answer. This has a vertical dilation of 8. The base is 2. Okay, let's do B. So here we have the x minus 2. Even when it's subtraction, because this is technically x plus a negative 2. Okay, so you still have addition. When you have addition, you're going to use the product property. So I can rewrite this as 3 to the power of x times 3 to the power of negative 2. Okay, 3 to the power of x cannot be simplified. but 3 to the power of negative 2 can. But the thing is you have a negative exponent, so we have to use the negative exponent property. Remember, the negative exponent property says you're going to take the reciprocal, so this is being divided by 1. So I can flip it around and do 1 over 3, and when I bring the exponent to the denominator, I'm going to make it positive. Okay? 3 to the power of x is now multiplied by 1 over 9, because 3 squared is 9. So my final answer would be g of x. I'm going to bring the vertical dilation to the front. My base is 3, and I'm raising it to the power of x. So that is the final answer. We have a vertical dilation of 1 over 9. Now let's do letter C. So again, I have addition in the exponent, so I'm going to use the product property. Okay. Now there's a 4 on the outside. That 4 is not also being raised to the power of x plus 2, because these parentheses here tell you that this x plus 2 is only being applied to the base of 3. So this 4 right now, I'm not going to touch it, but I will apply the product property to 3, and I'm going to do 3 to the power of x times 3 squared. Okay. Now we have 4 times 3 to the power of x and 3 squared, which is 9. Now remember, I told you you cannot multiply a number that is a base raised to the power of x. But we can multiply this 4 and the 9 because they do not have any variables on them. So to simplify, k of x would be 36 times 3 to the power of x. Okay, let's go to the next page. We can also use the power property of exponents to show that every horizontal dilation of an exponential function is equivalent to changing the base of the exponential function. Okay, so every horizontal dilation is equivalent to changing the base of that exponential function. So here in the parentheses, you can see we have a horizontal dilation. They're using a different letter, but that's okay. It doesn't matter what letter they use. Of horizontal dilation is anything, any constant that is multiplied by x, okay? And they're saying that you can change the entire base. So the entire base, the base is everything in the parentheses, okay? So example 3 says, which of the following functions is an equivalent form of the function y equals 9 raised to the power of 2x, okay? So right here we have multiplication, 2 times x. When you multiply, you have to use the power property. For the power property, remember I told you when you have multiplication, you're just going to cut through that multiplication with your own set of parentheses like this. Okay, so now this will become 9 squared to the power of x. So now you have a power raised to another power, which is what the power property says. We can multiply 9 squared, which is 81, to the power of x. Okay. Now, when we were getting started, we had 2 to the power of x, right? That means that b is the reciprocal, which is 1/2. So we had a horizontal dilation of 1/2, okay? But when we applied the power property, now we have a new base of 81, where this one, our base was 9. So how can that be? We started with a base of 9 and we had a horizontal dilation of 1/2, and we're saying that it's equivalent of changing the base all the way to 81. And now x is by itself. There's no longer a horizontal dilation. But they are equivalent. Let me graph it so you can see that, again, like the other one, they do overlap. So I'm going to add a new graph and I'm going to type 9 to the power of 2x. And I'm going to graph 81 to the power of x. Okay, and you can see they're both on there and they overlap. So even though they look different, they are still equivalent to each other. Okay, so the answer for this one would be letter D as in dog, 81 to the power of x. The last example says, which of the following functions is an equivalent form of the function y equals 9 times 4 to the power of x? Okay, this one is kind of hard because we don't have any horizontal transformations to go off of. So I'm going to use the answer choices to help guide me. Okay, so I'm going to simplify all the answer choices and see which one is going to give me 9 times 4 to the power of x. Now remember, the 3 on the outside is not attached to this 16 to the power of x divided by 2. This is by itself. So this 3, I'm just going to carry it over. And I can rewrite the x divided by 2 because I know dividing by 2 is the same thing as multiplying by 1/2 x. Okay? Now I can use the power property because I have multiplication in the exponents. So if I have multiplication, I use the power property. And the power property, remember I said just cut through the multiplication with your own set of parentheses like this. So this will be 3 times 16 to the power of 1/2, and on the outside you're going to have x. Okay, but now we have an exponent that's a fraction. Good thing we have a property for that. That's called the fractional exponent property. Which was on the first page. So I'm going to carry the 3 because I still haven't used it. What the fractional exponent property says is that you take the denominator of the fraction, and that'll be your root. And then you put the base, which is 16, on the inside, and the numerator of the fraction, which is 1, goes inside. And then make sure you carry the power of x. Okay. Now we have 3. The square root of 16 is just 4. Okay, so we're pretty close, but it's not perfect. Okay, so let's try letter B. A is not the correct answer. So we have 3. Again, that 3, we don't do anything with it yet. And then we have 16 to the power of 2x. But I see multiplication, so I'm going to cut through this multiplication and make my own set of parentheses. And now I can just write 16 squared inside and take the x and put it on the outside. Okay, 16 squared is 256 to the power of x. That is not the answer either. Let's try C. So again, that 9 doesn't have an exponent. I'm just going to carry it with me. And then I can rewrite x divided by 2 as 1/2 to the power of x. I can cut through the multiplication using the power property. I'm going to separate this and make a new base, which is 9 to the times 16 to the power of 1/2, and on the outside we have the power of x. I have to use the fractional exponent property again, which says the denominator of the fraction goes as my root. My base is 16. The numerator was 1, and on the outside I'm still raising this to the power of x. We have 9 times the square root of 16 is 4, and then to the power of x. Now this is what we wanted, so that means that C is the correct answer. Okay, now at first glance this lesson may seem easy, and it is if you have your notes in front of you and you're able to refer back to the properties. The challenge here is actually memorizing the properties, so take your time, make some flashcards, quiz yourself so you're able to use the properties without having to refer back to your notes. These properties will be coming up over and over again in Unit 2. So it is important that you take the time to learn them sooner than later so you can use them later on in Unit 2. Okay? Thank you so much for joining me today. I will see you in the next video. Bye.